Welcome to Part 5, Hashing. This topic is pure interview gold. If there is one technique that can instantly turn a slow, brute force solution into an optimal one, it is hashing. In this part, we will not just learn syntax, we will learn how to think in hashing patterns. Once this clicks, many interview questions will feel familiar instead of overwhelming. Why is hashing so important in interviews? Because most brute force solutions use nested loops. That usually leads to n-squared time complexity. Hashing allows us to replace searching with direct lookup. This single idea reduces many problems from n-squared to linear time. That is why interviewers love hashing problems. They test your ability to optimize. Let's define hashing. Hashing maps a key to a value. Instead of scanning data to find something, we jump directly to it. We trade extra memory for speed. This trade-off is intentional, and in interviews, it is almost always worth it. Under the hood, hashing uses a hash function. The hash function converts a key into an index. That index points to a bucket in memory. If multiple keys land in the same bucket, collisions are handled internally. As programmers, we do not manage this manually, but understanding that collisions exist helps explain performance limits. In C++, hashing is implemented using unordered map. Unordered map stores key-value pairs. You can insert a value, you can look it up, and you can update it. On average, all these operations run in constant time. That makes unordered map extremely powerful. Now let's compare map and unordered map. Map is implemented using a balanced tree. Operations take log n time, and keys are always sorted. Unordered map is implemented using hashing. Operations are constant time on average, but keys are not ordered. In interviews, unordered map is usually preferred unless ordering is required. When should you use map instead of unordered map? When the problem explicitly requires sorted keys, when you need range queries, or when constraints are very small and performance does not matter. Otherwise, unordered map is the better choice. Use unordered map when you need fast lookups, when you are counting frequencies, when you are checking complements, when you are solving array or string problems efficiently. This covers a large percentage of interview questions. Common hashing mistakes include using map by default instead of unordered map, forgetting that values can be negative, assuming hash maps are ordered, or forgetting to handle missing keys. Interviewers often test these small details. Now we move to the most common hashing pattern, frequency counting. This pattern appears everywhere, and mastering it gives you a huge advantage. The frequency count pattern is simple. We count how many times each element appears. Once we have counts, decision-making becomes easy. Instead of scanning the array repeatedly, we look up counts instantly. Let's look at an example. Given the array 1, 1, 2, 3, 3, 3, the frequency map becomes 1 maps to 2, 2 maps to 1, 3 maps to 3. Now questions like most frequent element, duplicates, or unique elements become trivial. In C++, frequency counting is straightforward. We iterate through the array. For each element, we increment its count in the hash map. If the key does not exist, unordered map automatically creates it. This simplicity hides a lot of power. Frequency counting appears in many problems. Anagram checks, majority element, finding duplicates, counting characters in strings. Once you see frequency counting, you should immediately think hashing. Now let's talk about toSum. This is one of the most famous hashing problems. You are given an array and a target. You must find two numbers whose sum equals the target. This problem teaches complement-based thinking. The brute force approach uses two loops. We check every possible pair. This takes n-squared time. For large inputs, this is too slow, and interviewers expect better. Here is the key insight. For every number, we ask a simple question. Have we already seen target minus the current number? If yes, we are done. If no, we store the current number. This turns the problem into a single pass. In the C++ solution, we use an unordered map. The map stores value to index. Before inserting the current value, we check if its complement exists. This ensures we find the pair efficiently without double counting. ToSum has many variations. Sometimes you return values instead of indices. Sometimes you only check if a pair exists. Sometimes the array is sorted, and sometimes you count all valid pairs. The core idea remains the same. Complement search using hashing. Now we move from pairs to ranges. Instead of two numbers, we look for a continuous subarray. This introduces a new pattern. Prefix sum combined with hashing. Subarray with given sum. We need a continuous segment whose sum equals the target. Important detail. The array can contain negative numbers. That immediately breaks the sliding window approach. The brute force approach tries every start index, and for each start, every end index. That results in n squared time. This is not acceptable for large inputs. Prefix sum changes the perspective. Instead of computing sums repeatedly, we maintain a running sum. The sum from index I to j is equal to prefix j minus prefix I minus 1. This mathematical identity is the key. Hashing makes prefix sum powerful. For each prefix sum, we check if prefix sum minus the target already exists in the hash map. If it does, a valid subarray exists. This reduces time complexity to linear. In the C++ solution, we store prefix sum counts in a hash map. The map tracks how many times each prefix sum appears. This allows handling multiple subarrays and negative values correctly. This is an advanced but essential pattern. Now let's look at longest consecutive sequence. Given an unsorted array, we must find the longest run of consecutive numbers. Order does not matter, and duplicates may exist. Sorting the array seems like an easy solution, but sorting takes n log n time. Interviewers usually expect a linear time solution, so sorting is rejected. The hashing insight is clever. We insert all numbers into a hash set. Then we only start counting a sequence when the previous number does not exist. This guarantees each number is processed once. In C++, we use an unordered set. For each number, if number -1 does not exist, we expand forward. We count how long the sequence continues. This gives an O of n solution. Let's recap hashing patterns. Frequency counting, complement search, prefix sum with hashing, set-based scanning. If you can recognize these patterns, hashing becomes automatic. And once hashing becomes automatic, many interview problems stop being hard. Next, we move to trees.